Hi, I'm Dr. Pamela Britton, and I'm joined here today by Ann Kajander, who's going to speak a bit more on her article for the journal entitled The Mandate of Scholarly Mathematics Education Research, Moving Ourselves Forward. This is part two of our interview, so I highly encourage you to watch part one first, as this discussion will be providing some additional context and insights from that interview. Thank you once again for joining me. In our first interview, you made the claim that math anxiety doesn't exist. And if we want to really address math content in our schools, we need a different label and a different approach. Can you expand a little bit about on that?
Yeah, so what we talked about in the first interview was the importance of developing deep understanding, and that's what provides the comfort. So I think the issue is that the idea of an anxiety or a fear is a side effect of the fundamental problem. It's not in and of itself the problem. The problem comes from people developing the sense that mathematics is something difficult to understand. It's about rules that have to be memorized. There's this suspension of sense making because perhaps they've had an experience where something that made sense to them in the past, they were told that, oh, that's not the way to do it. So they develop this false sense that, well, math isn't, it doesn't have to make sense. I've literally had students say that to me. Well, it doesn't have to make sense. It just has to follow the rules. And so, of course, that's going to generate this feeling of sort of discomfort and disconnect, and also a sense that, oh, I don't understand it, so I must not be good at it. And so I think the best way, the best antidote for those feelings is to develop a sense of what it means to understand it and see how that changes your perception of yourself as a math learner.
Excellent. Um, Now, there's a lot of debate in our schools, in our society, in our with our politicians, and everybody seems to have. You brought this up in our first interview. Everybody kind of seems to have an opinion on mathematics. Um, so, what should our schools be focusing on? Is it rote math? Is it, discovery math, which is kind of a catchphrase? Should we be going back to basics? Obviously, we can't teach everything. So, kind of from your research and in your opinion, where should our priorities lie? What should we be focusing on? And I guess also, what should we be looking to let go of? In our math curriculum.
I think there's this sense that we need to hang on to all of these different kind of computational things because that's what we all learned about math. So it must be really important. And nobody wants to admit that maybe we learn things that are perhaps not quite as important anymore. So we want to hang on to them because it somehow is tied up with our sense of what we ourselves experienced. So let me give an example, and this will no doubt date me. When I was in grade 9 or 10, we learned a computational procedure for finding by hand the square root of numbers that were not perfect squares. So for example, we were perhaps given a number like 18.4 and asked to find the square root of that using a particular computational procedure called Newton's method to however many decimal places. Now, that's not in the curriculum anymore. So to say that we haven't let go of some computational things is untrue. We absolutely have. The argument is, where's the line, right? What do we need people to know computationally? And what do we need people to know conceptually? So I'm not suggesting we shouldn't know anything about squares and square roots. I think it might be important to know that a 4 by 4 square is like 16 little unit tiles. And a 3 by 3 square is 9 little unit tiles. And so therefore the square root of 9 is like the edge of that square, which is 3. The square root of 16 is like the length of the edge of that square, which is 4. And so if I asked a student, well, what's the square root of 10? They might be able to say, well, 10 is bigger than 9, so it has to be bigger than 3, but it's smaller than 16, so it's going to be less than 4. So it's just over 3. And from there on in, they're going to use technology. They're not going to work it out by hand using Newton's method. So we have let some computational things go. And I think that's appropriate in the age of technology. But what we need to have more than ever is an understanding of the meaning of those ideas. I would like students to know that the idea of a square root is, for example, the side length of a region that has that area. Conceptually, visually, to have a sense of what it's for, rather than just it's this weird little obscure symbol on my phone or my calculator.
Excellent. Yeah, it's definitely it's more about the art of understanding and you made a perfect with the estimation. We don't need to necessarily know the exact number to start with, but we need to be able to figure out how do we get there. Um, so there's definitely a focus on kind of building understanding, and you actually promote kind of doing that through modeling concepts. In fact, you've actually written a book called Mathematical Models for Teaching Reasoning Without Memorization. Can you tell me a little bit more about that book?
Sure. I want to say I was persuaded to write that book by a wonderful colleague and at the time classroom teacher who became my contributing author uh, to the book, who insisted that because I was doing this work and there wasn't another resource that went into this kind of depth, particularly around the intermediate content, that it really needed to be put together into some sort of resource. So the um, the idea of the book was to support, in particular, teacher candidates, but really it would work for anybody that would like to understand some of the fundamental methods that we learn, particularly in elementary uh, and middle school, that historically were taught without necessarily students being shown how the methods worked. And that lack of understanding of how or why the methods work is also what contributes to people's sense of um, feeling uncomfortable about mathematics.
Perfect. Now this question's kind of a kind of last question's kind of a bit of a side tangent. You yourself, you have a background in mathematics, and you are also a mathematics education researcher. Um, can you speak a little bit about kind of the differences there, and how that's kind of shaped your research and kind of how you've approached things and I guess kind of the differences between mathematics and math education and where they intersect as well.
Sure. Um, yeah, so as you mentioned, I began as an undergraduate student in a degree in mathematics and computer science. I actually worked as a computer scientist for a couple of years in industry. And those disciplines are scientific disciplines. Um, Mathematics itself is rooted in the notion of abstract ideas, of that kind of thing. So when I made the decision to move into education, and that was kind of a gradual process. As I worked in industry, I had gotten more involved in doing workshops and things within the company that I worked for, and I realized that that was really what I enjoyed, was working with people and supporting their development. So I made the switch into education, and it really was a switch. It was a switch in content, but also very much a philosophical switch. There are this completely different environment to be focusing on human development and cognition compared with being focused on more abstract kind of scientific ideas. So that really was a change for me. And I'll think of myself now as a mathematics educator, that is someone who is interested in how people learn math and what mathematical understanding is, and in particular, working with pre-service teachers and helping them to understand the mathematics better. We talk a lot about problem-based learning and these kinds of things, but the difficulty with problem-based learning is unless you understand the mathematics well enough, it's very difficult to support. So if your only understanding of a particular mathematical idea is a formula, then of course, as a teacher, it's going to be very difficult to design an environment and support students developing deep understanding and reasoning. So it has become a passion and a focus of mine to help particularly pre-service teachers develop that deep understanding. And one of the most recent pieces of work that we've done, and this is also a quite recent article in the Canadian Journal of Science, Math, Technology Education, is looking at pre-service teachers who had math degrees and trying to probe into what their level of deep understanding of elementary concepts is. And it was well, not surprising for those of us that have worked with them, but perhaps surprising to other people to reveal that even people with a math degree don't necessarily understand the underpinnings of some of this kind of more basic or elementary mathematical work that they are then going to be involved with helping students understand. So it's something that is really important for everyone involved in education to develop.
Yes, completely understand, and agree. I think there's a lot definitely there with pre-service, um, with teachers, and the people teaching the math, and what their beliefs are, and that. Are there any final thoughts that you'd like to kind of leave us with today? We've touched on a lot of different topics, and I think this is a very um, current issue, but I think it's a long running current issue. I think it's been a current issue for a very, very long time. So are there any kind of final thoughts that you'd like to leave, um, based on kind of what we've discussed, or anything else that you've come up with in your research?
Perhaps could I leave you with two just small mathematics examples from classroom learning? Because sometimes when we talk in generalities, it's easy to not be clear about what exactly is being said. So I want to give just two quick examples, if I may, from classroom teaching and learning. The first one happened to me as a high school math teacher prior to my joining the Faculty of Education full time. And I was teaching a grade 12 course. It's in Ontario, sort of informally called the apprenticeship math course. This is for students that are heading in that direction, typically to a community college or so on. And so some of these students have not necessarily developed a great sense of themselves as mathematics learners. And early on in the course, I asked just some very sort of broad-based math questions, computational questions, trying to get a sense of where these students were at and what their level of understanding was. And I remember one of the questions that I asked, just typical elementary school fractions question, 1/2 plus 1/3. And so if you think about what 1/2 is in your mind, you have a mental image of what is 1/2. I had some students not able to answer it. I had an extraordinary number of students tell me that the answer was 2/5. So really not remembering that procedure that they no doubt learned, and willing to grab onto any procedure they kind of vaguely remembered. So in multiplication, you do some stuff. So maybe you add the numbers in the top and the bottom, I don't know. And they came up with this answer of 2/5 that is actually less than even just one of those initial amount. So 2/5 is less than a half, and yet they're adding something onto 1/2. They were completely willing to let go of any sense making to grab onto some possible procedure that might or might not have been the right thing, but unwilling to trust their own sense of what the numbers might mean. Except one young man who I happen to sort of know had a job at a garage, in fact, and he wrote on his paper, I don't remember the method, but I know that these are about zero point 0.5 and zero point 0.3, and so I think the answer is about zero point 0.8. And I thought, great, you have number sense. You know approximately how big these numbers are, and you can give a reasonable answer. You also know sort of the limits of what you do and don't know. So I was actually happier with that answer, even though, okay, maybe it's off by, some very small amount, but that at least there's this sense of knowing what the quantities are. Fast forwarding that into university level mathematics for pre-service teachers, the kinds of experiences that I have found helpful for pre-service teachers, and I'm just giving that teeniest tip of the iceberg here. This would be the very, very beginning of a half course in mathematics for elementary teachers that is uses some of the methods in the book that you refer to. So for example, if you give students some manipulatives, and these are just very quick handmade manipulatives of something like 2/3, right? So we take some pieces of plastic and we say, well, these are 2/3, and we make sure that students know what that part whole definition of a fraction is, so that they know that the 3 means there's 3 parts in one whole, and the 2 means there's 2 of them. And then I say to people, well, can you show me what half of that is? Show me half of this much. And so there's sort of 2 reactions, right? Some students madly take a little corner of their notebook, even though I've told them not to write down, and they multiply 1/2 times 2/3, and they get a whole bunch of numbers that they multiply, and then they have to simplify, and they do all this little work, and they get some sort of answer. And other students tentatively say, like, really, you mean like 1/2 of this, like 1/2 of it, like, yeah, really, I really mean 1/2 of it, like there's a half of it. And then they say, what? It's that simple? That's it? And then, they look at this little computation thing that they've done, and maybe they got an answer of 2/6, and they say, well, that's more complicated. Like, yeah, it is. It's unnecessarily complicated. We don't always need the traditional algorithm. Sometimes we can just actually use reasoning, and it works better, and it makes sense. And such a simple little 2-minute experience, which we then build on, of course. We don't stop there, and we build on more complex and more in depth and more robust understanding. But that starting point can be enough to have people say, "Oh, I get that," and that's really the entree that lets you move forward.
Oh, I think that's wonderful, and if we can get teachers to see that, then we can get them to get their students to see that, which I think is probably one of the most powerful aspects, definitely, because teachers are going to influence thousands of students over their careers. So, um, well, I think that definitely gives us a lot to think about. And thank you so much for taking the time to do not one, but two interviews regarding your work. But I think it's such a timely and an important topic and concept. Um, Once again, you can read Dr. Kajander's article, The Mandate of Scholarly Mathematics Education Research, Moving Ourselves Forward, online at springer.com/42330. You can also find information about her book as well. Um, for the Canadian Journal of Science, Mathematics, Technology, Education, I'm Pamela Britton, and I'd like to thank you for joining us today. And of course, don't forget to follow us on Twitter at CJSMTE.